Welcome to this explainer. Today, we're diving straight into the fascinating math and software engineering behind unitary evolution recurrent neural networks, or URNNs for short. If you've ever wondered how we can elegantly force a neural network to remember information over incredibly long sequences without its entire mathematical foundation collapsing, well, you're definitely in the right place.
So, let's kick things off with a fundamental question. Why do deep neural networks struggle so much to retain information over hundreds of steps in a sequence? I mean, think about it. When we're feeding a network data point after data point, say like reading a really long book or processing a massive time series, the network has to constantly update its internal state. But standard models have this terrible habit of essentially getting amnesia when the gap between the relevant info and the current step gets too large. Today, we're going to explore exactly why that happens and how an absolutely ingenious combination of complex math and clever software engineering actually solves it.
Here's our roadmap for today's explainer. First, the RNN memory bottleneck. Second, the power of the identity matrix. Third, the unitary matrix solution. Fourth, engineering the URNA architecture. And fifth, proving long-term memory. Let's jump right in.
Part 1. The RNN memory bottleneck and the exact limitation of standard models. When a network processes a sequence, it's repeatedly multiplying its hidden state by a weight matrix at every single time step. Now just imagine taking a number slightly less than 1, like 0.9, and multiplying it by itself 100 times. It shrinks away to almost nothing, right? It's literally like playing a massive game of mathematical telephone, where the signal just entirely fades away. We call that the vanishing gradient problem. On the flip side, if your weights are slightly greater than 1, say 1.1, doing that same multiplication 100 times makes the numbers absolutely explode into chaos, which totally breaks the training process. This exponential decay or growth is the foundational bottleneck that stops standard RNNs from learning those long-term dependencies.
Moving to Part 2, the power of the identity matrix, which gives us our theoretical fix.
So, how do we fix this exponential decay or growth? Well, the theoretical fix starts with a foundational math concept called the identity matrix. This is a special square matrix where if you multiply any compatible matrix by it, the original is left completely unchanged. It's basically the matrix equivalent of multiplying by the number 1. If you repeatedly multiply a state by the identity matrix, it neither vanishes nor explodes. It just stays perfectly preserved.
And this property is absolutely crucial. Because the product of an identity matrix remains unchanged, gradients can just flow unimpeded backward through time. Modern architectures like ResNets actually use this exact logic implicitly, relying on skip connections to keep their deep network stable. But here's the catch for a recurrent neural network. Just using a static identity matrix isn't enough, because a static matrix can't actually learn anything new. We need a matrix that preserves signals perfectly, just like the identity, but is still flexible enough to learn complex, changing patterns.
Which brings us to Part 3, the unitary matrix solution, and moving into the complex domain.
To build that adaptable network, researchers turn to the unitary matrix. Now, the absolute key takeaway here is that a unitary matrix is a complex-valued matrix where the eigenvalues have an absolute value of exactly 1. What does that actually mean? Well, in plain terms, when you multiply a vector by a unitary matrix, the length, or the norm, of that vector never changes. It might rotate around in a high-dimensional complex space, sure, but it will never shrink into a vanishing gradient, and it will never explode into an infinite 1. It's really the mathematical holy grail for recurrent memory. But, of course, there's a massive roadblock. It's one thing to say, hey, let's just use unitary matrices. But actually forcing a matrix to stay unitary while a neural network updates its weights during training, that's incredibly difficult. It typically requires a math operation called eigendecomposition, which is essentially taking the matrix apart into its core frequencies. If your hidden layer has size n, doing that decomposition costs an impossible O(n) cubed in computer memory and processing time. For modern deep learning, that is just way too slow and resource-heavy to ever be practical.
So how did they fix it? That's part 4, engineering the URNN architecture to make the math run efficiently.
The solution here is just an absolute masterclass in AI engineering. Instead of using one giant computationally heavy matrix and trying to force it to be unitary, the researchers built their weight matrix by multiplying several smaller, highly structured unitary matrices together. By chaining together diagonal matrices, reflection matrices, fixed permutations, and Fourier transforms, they created this brilliant workaround. Because, you see, the product of any unitary matrices is always another unitary matrix, so the final result is 100% guaranteed to be unitary. By operating on these specific, simple matrices, they slash the computational cost from a crippling O of n cubed all the way down to just O of n log n, while keeping the memory footprint super tight at exactly O of n.
But wait, there was another major engineering hurdle they had to cross. Most standard deep learning frameworks at the time, like Theano, which they were using for this research, just didn't natively support complex numbers. So the engineers had to get creative. They essentially treated every complex number as two standard real numbers, a real part and an imaginary part. They mathematically split the vectors and the matrices and then calculated all the cross multiplications natively using standard real number operations. They literally tricked the software into doing complex domain math using only standard real number pipelines.
And they couldn't stop there either. Neural networks need activation functions to learn complex patterns, right? The standard choice is usually the ReLU. But standard ReLUs just zero out negative numbers, which absolutely brutally destroys the phase or the angle of a complex number. And since that phase is exactly where the URNN stores its long-term memories, applying a normal ReLU would completely ruin the whole architecture. So the engineers had to design a custom activation function from scratch called modReLU. It only affects the absolute value of the complex number, leaving its critical phase perfectly intact.
All right, on to our final section, Part 5, proving long-term memory where the data speaks for itself. Check out the copying memory problem. This was tested with a massive time lag of 500 steps. Basically, the network is shown a sequence, fed 500 steps of blank noise, and then asked to perfectly recall the original sequence. If you look at the green line, which is the industry standard LSTM, it completely flatlines. It's honestly no better than random guessing at that point. Its memory has entirely saturated. But look at the blue line, the URNN. It plummets to near zero error almost immediately. It completely solves that 500-step time lag without breaking a sweat.
To understand exactly why it crushes that problem, we just need to look at the gradient norms after 100 training iterations. This gives us our definitive mathematical proof. These norms represent the strength of the learning signal as it passes backward through time. See the LSTM's green line? The gradients decay dramatically as we look further back. But the blue line for the URNN stays incredibly strong. This proves definitively that the unitary math is working. Information is successfully propagating back through hundreds of time steps without vanishing.
Finally, let's look at a highly complex real-world test, the permutated MNIST dataset. In this test, an image of a handwritten digit is unrolled into a flat sequence of 784 pixels, and then those pixels are totally randomly shuffled. The network has to read them one by one and try to guess the digit. The URNN reaches over 91% accuracy in just a fraction of the time it takes the LSTM. And even more impressively, it accomplishes this state-of-the-art result using only 9,000 parameters, compared to the LSTM, which needed a bloated 60,000 parameters. I mean, that is a massive leap in efficiency.
As you wrap up this explainer, seeing how beautifully the math aligns with the software engineering here really leaves us with a provocative thought. Right now, the AI industry is completely obsessed with just throwing more parameters and more compute at our memory bottlenecks. But as the RNN shows us, a smaller model engineered with flawless mathematical constraints can radically outperform those larger brute force models. So how much more powerful will our systems become when we stop just scaling up and actually start engineering smarter? Thank you for joining me on this deep dive. Keep questioning, keep learning, and I'll catch you in the next explainer.